Okay, guys, this is our fifth session. So what I did for you this time, I thought we'll pick some topic really. I think it's interesting to all the designers and engineers, which is the motors. So I have a PowerPoint presentation that's going to talk about just the basic, like when Dave and I talked, you mentioned a few things about just the basic construction of things and so forth. So I have a presentation about basic motors and motor control and construction and so forth. And then, so that's the PowerPoint presentation. Then I do have 4 sheets that looks like this. These are examples of sizing the overcurrent protection device, the disconnects and so forth for all of you. So I thought that would be a good, here's an example of it. Looks something like this. 4 sheets of this, and they're numbered worksheet 04. And then, so that's going through all the code requirements for the design. And again, you guys are as smart as I am, if not smarter. So if you find something that doesn't make sense, please bring it to my attention. I'm a human being like everybody else, make mistakes all the time. And I also did a 3 coordination, overcompetition coordination and overload protection coordination for 3 motors. These are the curves they're going to see at the end. So that's kind of my plan for you. So any comments, guys, about what we've done before? Anybody has any comments, concerns? Everybody's okay? Cool, kinda? Okay, so let me go ahead and start with my PowerPoint presentation. Talk about motors. Please inject your ideas at any time. We have the 2 hours, so I'm going to go ahead and start about motors. Motors and motor control, guys, we are not motor people. We're design engineers like all of us. So we need to know enough about motors to be dangerous. That's how I always call it. So it's really nice for us to know the basic construction of motors, the types of motors that used typically in the industry, from the AC induction motors into the DC and the synchronous motors and so forth. So I'm not a motor guy, and don't expect me to give you every ins and outs of maintaining the motor. So this is just an overview. As a designer, when you walk into a building, you need to understand a few things about motors and motor controller. As far as we're concerned, design engineers, we walk into a building and every mechanical equipment has some type of a motor in it, right? So we need to, for us, as far as we're concerned, we need to power this piece of equipment. We need to disconnect this piece of equipment to work on it safely. We need to protect it from overload, protect it from short circuit, and be able to control it. Start it, stop it, ramp it up, ramp it down, speed control it, and so forth. So that's what this class hopefully is geared for. I thought we'd start with the squirrel cage. Let me before I go ahead. Dave, do you guys deal with synchronous motors? Not a whole lot. DC motors? A lot of like cranes. Okay, so the focus is mostly squirrel cage induction motors. These are most common motors that we're going to be dealing with. It's squirrel cage induction motors. A few things about squirrel cage induction motors, guys. When it comes to motors, it's really a few things about the difference between a DC motor and an induction AC motor and a synchronous motor. This little manual that I keep bringing with me, it gives you enough info to be dangerous about different type of, like, which one is better in terms of starting. When it comes to specifying motors, I don't think you guys get involved in it. Typically, mechanical engineers will get involved in specifying the type of motors with the mechanical equipment. But for us, I found it as an engineer, it's really nice to know a few things about them. At least we speak the same language. So good starting torque. When it comes to motor, the single most important thing is the ability to be able to start starting torque, so it doesn't stall when you start that machine. And if you're dealing with air handling unit and all this good stuff, is not a big deal. But when it comes to conveyors and multiple things, they have a heavy load on them. Starting torque of a motor as well as a running torque of that particular motor is a big deal. So when you deal with squirrel cage induction motor, very simple. It has the stator. I don't know if I just had a cut through here with the stator winding. So they have a couple of windings. They hook them up in a delta or a Y, and then in between them they have a chunk of steel that rotates, which is called the rotor. And in order to facilitate the mechanical operation, the smarter than Chad decided to put some bearing there because to facilitate the mechanical operation. So that's really not a whole lot of it other than a chunk of steel rotating inside a bunch of coils that are connected in a delta or a Y, typically a Y connection motors. and it is a magnetic machine. So what happens is you bring your electrical energy in here, and as your electrical energy gets into the machine, and get back to the basics, as your electrical energy comes in here, I'm talking about energy power, your mechanical energy comes out of this machine out. So this is the, as far as I'm concerned, is electrical to mechanical energy or power conversion machine, right? That's what we use them for. So how does that magic goes? It very quick. You energize these coils. They create a magnetic field. The magnetic field of the coils induce voltage into that rotor here. The induced voltage, because it's shorted, it's a squirrel cage induction motor shorted at the end, the bars, create a current. That current creates another magnetic force inside the rotor. Now you have a magnetic force in the stator, magnetic force in the rotor, and when you have two magnetic poles opposing each other, they're going to pull away from each other, or pull together if they're opposite polarity. So that's basically the concept of spinning inside a motor. So this is probably, and correct me if I'm wrong, guys, probably most of the mechanical equipment that we handle in buildings is made of some type of a squirrel cage induction motor. Any comments, guys? Any questions about that? So when you have, here's your 4-pole here. So as you induce, you create a north pole right in here, the induced voltage, and obviously with 2 poles, magnetic poles, close to each other, they pull away from each other and start that magic spinning mechanism that we call it rotation. Any comments about this, guys? Down to the basics. So I thought that's down to how the squirrel cage induction motor works. Take electrical energy converted to mechanical energy. This is probably one of the most important things for the mechanical engineers. That's how you can convert the electrical energy into mechanical power, torque, pound per foot. So you take your horsepower, you multiply by this magic number 5252 and divide it by the RM, the speed of a motor. That will give you how much torque that motor can handle. And I don't have the mechanical formulas. The mechanical guys take the torque and convert it into mechanical power, and then size their belts and whatever they need to do. So that's very, very important for the mechanical engineers. For us, electrically speaking, this is the most important info that we have. This is how you can find the full load amp of a motor, a formula that can get you a full load of an amp motor. So if you have a 100 horsepower motor, you convert it into kilowatt by multiplying by 746, divided by the voltage and its modifier, 1.73 because 3-phase, and then divided by the power factor and the efficiency, and you got yourself the nameplate full load current if needed. The nameplate full load current if needed. So these are electrical formulas. So this is my mechanical formula here. I thought important to do. This is my electrical formula for full load amp. This is called the full load amp, that nameplate. But I think, personally, I think one of the most important ones is this guy in here, which is right in here when it comes to controlling any motor. So SS is your synchronous speed. The synchronous speed of a motor, which is the speed of the magnetic force, SS, synchronous speed, equal 120. That 120 has to do with the frequency, multiplied by F is the frequency divided by the number of poles. Why it's so important for us, this formula? This formula has 2 things. In order to control the speed of a motor, if you want to control the speed of a motor, you have only 2 options to control the speed of a motor. Option number 1, which they used in the past, changing the poles. Now, if you change the poles, meaning the windings inside the motor, you have 2 coils. You energize 1 set of coils. That set of coils will give you speed 1. That set of coils will give you speed 2. You energize both of them at the same time, will give you speed 3. That's how they used to have speed control on motors, by changing the number of poles inside the motor. The disadvantage of this, a lot of wires inside the motors, of course, a lot of leads coming out of the motor to rewire them. Now, in for the last, 20 years am I supposed to say here? 20 years or so, they have been manipulating the frequency, and that's the birth of the VFDs. Now, if you look at the frequency here, if you change the frequency, take it up, the speed goes up. If the frequency down, the speed goes of this motor down. That's the fundamental, basic understanding of VFDs. Manipulating the frequency in order to manipulate the speed of that motor. Any comments, guys, about this formula and why I picked it? Because that's the birth of the VFDs, basically. You manipulate the frequency, you get yourself control to the speed, of course, with the frequency. Because of the inductance, we also manipulate the voltage.
Any comments, guys, about these? I keep asking. I threw these. These are typical symbols that you're going to use and you're going to see in electrical and control symbols. And I'm not going to go over a lot of them, guys. Do you guys do a lot of control, motor control? Get involved in motor control, point-to-point wiring for motor and control, the control circuit.
Yeah, we do. We're not at.
Okay. So now if you do schematics for motor control, that's a whole different animal. I have a couple of schematics, very simple schematics for you, so you can go from, so these are used when you do motor control schematics. When it comes to motors, there are two very important circuits for every motor. Circuit number one is the power circuit, dumping the electrical power into the motor to convert it to mechanical power. Very simple. 3 wires coming into the motor to bring that 3-phase power to convert it to mechanical power. The second circuit is, I think it's the most important and the most complicated one, is the control circuit. That control circuit could be a magnetic starter. We have a couple of examples here. Could go from as simple as a magnetic starter sitting there with a push buttons all the way up to the top-notch VFD. And in between the soft start and a bunch of other things. So all these symbols, I thought just to throw it here without going over them, just to show you, these are the symbols that you're going to be encountering if you are to do reading schematics for motor control like air handling unit or chillers or or any of these motors that you need to control. If you guys, I did wastewater treatment plants for short tenders, and now I remember them. And they used to do a lot of, they're not far away from me, are they? Right here. And they used to do a lot of, another set, one set is electrical drawings and the other set is control drawings. Didn't work good for them though. So that's kind of the symbols I thought to get you through. Again, the class is not meant for schematics. If it's schematics, we'll take a lot of these guys and we'll manipulate them, work with them. But I thought this is just FYI. That's what you need to do. All these symbols, guys, in a lot of online and a lot of books if you want the full list. Okay, so we know the induction squirrel cage induction motor is the single most important motor you're going to encounter in a design environment. So I listed, after we know how it works, that motor, now we need to know how to control that motor. Controlling the motor, guys, so I listed a couple of things, motor controllers that you're going to encounter. Controller number one is called manual start-stop. Manual start-stop, you have a fan in the bathroom, and the switch in the bathroom can turn that fan on and off. That's your manual switch. There could be a snap switch, sized appropriately to control the fan in the motor. It goes all the way up into a contactor that you can push physically. It's like a push button. I don't know if you guys have seen them, we use them. A push button, you push, instead of turning on and off a coil, you can turn on and off the phases, the contacts. Physically, mechanically, you turn them on and off. That's a manual controller. I don't think you guys put a manual controller in an air handling unit. And my experience with the controllers is typically specified by the mechanical engineers, which is in-house for you guys. So it's good to understand. You would not put a manual controller in an air handling unit. The second, so that's kind of the poor man's way of doing business, manual controller. Then you get into the magnetic starters. Magnetic starters is the second step up. Magnetic starters, you guys, you see these all the time. They call them FVNR, full voltage non-reversible. You have a magnetic starter, you energize a coil, the coil slam multiple contacts shut, and when they slam them shut, the motor will rotate in one direction, full voltage. You would not manipulate the voltage. That's why they call them full voltage non-reversible. So when you turn that magnetic starter on by pushing the start button, you apply the full voltage, the 480 or the 208, right across the terminals of the motor. That's where the word full voltage coming. No manipulation of the voltage, no reduction in the voltage, and non-reversible, it just goes one direction. So that's the simplest one that you can do. And then the nice thing is then you can interface this one with any control system that you can have from your laptop into anything you want to remotely control that motor if you can capture the coil. This is exactly across the line. Full voltage, non-reversing is across the line. Across the line, you do not reduce the voltage. You have that term later on. Thank you for reminding me. The other one is full voltage reversible. The difference between that one, that's full voltage, the same across the line, but it goes both directions. These are all magnetic starters. The second one is 2-speed, 2 windings. So they have 2 windings inside the motor. And by energy, they take two magnetic starter. By energizing one set of windings, it gets you one speed. Another set of windings give you another speed. So that's kind of speed control on the motors. This one is reduced voltage auto transformer. Now, up to this point, you're dealing with across the line, what we call it across the line, because there's no manipulation of the voltage. Now you go down into RVAT, they call it reduced voltage auto transformer, and there's multiple methods of reducing the voltage. So reducing the voltage, instead of, I always say, when you apply a 480 across any machine, can you imagine the amount of torque, mechanical torque that's going to shake this machine, the starting torque for that machine, if it's not rated for it? So there will be a huge amount of torque, starting torque, that could damage the machine, number one. And number two, there's also a starting current that could interface with your electrical power system by sucking more energy from your system, and your lights will dim. So the Smarter Than Chad years ago decided, if we have motors probably larger than 15 horsepower or so, or 30 horsepower, it's a good idea to apply a voltage reduction. So what they do, here's the 480. They cut the 480 momentarily for only up to 10 seconds, cut it down to half of it, 240, apply across the motor. Now the motor, instead of getting a big oomph when it starts, mechanical oomph, mechanical stress on the equipment, and electrical stress, pulling a lot of current and dimming the system because of voltage drop, the starting current. So they manipulate the voltage, reduce the voltage. By reducing the voltage momentarily, you reduce the starting torque, the mechanical stress on the equipment, and you will reduce the electrical stress on the equipment by reducing the starting current. So that's the whole idea of reducing the voltage. So you can do this one through auto transformers, through inline resistors, inline reactors. I'm sorry, do you have any question, guys? So that's the voltage reduction. So the first set here, what we call them, is across the line. All these are across the line. Then this one becomes voltage reduction, reducing the voltage. So you can reduce it electrically by auto transformer. There's also resistors and reactors you put in line. I'll show a couple of examples of it. The second one is called the electronic motor controller. The electronic motor controller, you guys use them, probably a lot of people right now use them. The notoriously famous one is SSRV, which is solid state reduced voltage. Solid state reduced voltage is nothing other than an auto transformer. It creates an image of it manipulates the voltage, reduce the voltage like an auto transformer or inline resistor to reduce the mechanical and electrical stress on the system, and it does a couple of other things too. So instead of reducing the voltage by having an auto transformer or a resistor, they reduce the voltage by manipulating the signal itself electronically by power electronics. So that's your next step up for voltage reduction. And of course, the Cadillac control for motor is VFDs. VFDs will get you a reduction on, it will reduce the voltage, so no mechanical and electrical stress in your system, and at the same time, it will give you multiple speed control. It will give you speed control. Variable frequency speed. Or controller, VFDs or variable frequency speed, I think. That's for speed, isn't it? Yeah. But the concept is manipulating. Yeah. Drive is for the AC. So that's, yeah. Yeah. These acronyms is from Square D. The acronyms directly from Square D. VFD, yeah. Well, VFD is there's a term, yeah. Variable frequency speed, variable speed control, variable frequency drive. You cannot describe a DC drive as a variable frequency drive because there is no frequency for the DC. So then the DC drive, they call them AC and DC drives. And the AC drive is VFD. A DC drive is they manipulate the DC because there is no frequency on it to do the same thing. So that's where the I think the term that we use is the AC drive and DC drive is the most common kind of major division between AC control and DC control if you have DC motors. Any comments, guys, about these? So that's kind of a back to the basics. So really, every time you have a motor, in the back of your mind, there are two things we need to do to the motor. Number one, we need to reduce the starting current and the starting torque of this motor to reduce the mechanical and electrical stress on our mechanical and electrical system. And number two, if needed, I need to control the speed and the rotation of this motor. The speed by running it at multiple speed, if needed, that will get you into the VFDs or multiple coils to energize. And rotation, if needed also, the VFDs will get you different rotation, or you have to have, like I said, a full voltage reversible that you can reverse the rotation of that fan. So blows air in or blows air out.
In our specs, typically in our tank 1 through 4 is the manual, and that's either surface or flux mode. And just in our specification when we picked our starters, in the magnetic starters are the 5 through 7.
Are you talking about NEMAs? The NEMAs?
No,
or 5?
Our tanks, and we edit our specs.
I see.
And I don't know if the edit the specs, but in there, that's how we identify.
I see what you mean.
Which ones are magnetic versus manual starters, and then we have type.
Okay.
The VFDs, so.
Okay. And full voltage, non-reversible and reversible, I believe they go from NEMA 0 and all the way to NEMA 9, depending on how much horsepower you have. The higher the horsepower, the higher the NEMA size that they have. Okay, so that's what I thought. Here's the symbol across the line, like we just said. This is the simplest, cheapest way of controlling a three-phase motor or a single-phase motor. Your magnetic starter is locating right in here. And here's your power circuit. The power circuit is coming at the top. Your control circuit is coming right. We'll talk about all these are part of my control circuit. So you close, very simple, you close this contactor here, you drop the current right across the coil. Now this coil is, say it's powered with, let's just say this voltage was 480. So this coil now is energized with 480. When it's energized, it locks that contactor, shuts that contactor, because mechanically, physically, you know how the coil works. You energize a coil and coil is attached, physically, mechanically, contacts attached to it. When you energize it, it closes these contacts, as many, 5, 4, typically 4 or 5 contacts that you have. You energize the coil and push them mechanically to close. So when they close, then your motor will receive the power. Bam, and here and here. So now my motor is up and running. You come over here, you push this button down. Very simple. You push it down. This is your stop button. You interrupt the control circuit. The 480 is gone across the coil. The coil is very important. That little coil here. No 480 across the coil. Then it de-energizes. Then it will open these contacts. The contacts will open because they're not held by the coil anymore. Any comments, guys? This is your across the line. This is full voltage non-reversible. You're looking at a full voltage non-reversible. NEMA 0 through NEMA 9. So that's, I thought, start with that one. You're looking here at a full voltage reversible across the line, a controller for a full voltage reversible. This looks like NEMA 0 here, but you can, here's the NEMAs, looks like this. They're contactors and overload at the bottom. They have their overload adjusted down at the bottom. So the only difference between full voltage reversible, full voltage non-reversible, the reversible, guys, will have 2 sets of contacts. When you push one button, you energize one coil that pushes 1 set of contacts called the forward. When you energize the other one, it will energize another coil, which in turn it drives a couple of other contacts. So you can see all the, I don't know if you guys are familiar with schematics, reading schematics. Every coil has a number or letter. Like for example, here's this coil is R. So all the contacts that are labeled with R will be physically, mechanically driven by this contact. And there's a lot of, there's a couple of mechanical and electrical interlocking here. So you know, when we reverse a 3-phase motor, we reverse 2 phases, 1 and 3, right? So what happens if you reverse and forward the motor at the same time? There is no mechanical interlocking or electrical interlocking. You get a dead fault between phase A, phase 1, and phase 3, right? Or phase A and phase C. So that's where they have the mechanical and electrical interlocking. So when you forward the motor, mechanically you open the reverse. And at the same time, electrically you isolate the reverse circuit. Any comments, guys? Any questions about this one without turning it into schematic reading. So for us as an electrical engineers and designers, guys, unless you do control, that's probably as far as we can go in terms of understanding them. A couple of things about the control circuit. The code has a few requirements about the control circuit. Typically, these are with, I don't know if you guys get into the line side of the control circuit here, you know, when to ground it, when not to ground it, how far you can do it. But these typically are inside the controller itself. All this junk is inside the controller, and we bring the power to it. But it's nice to know how it works, though. Any comments, guys? Any questions about that? Comments? Full voltage, reversible. So you hear this one, full voltage, reversible. It goes in forward and reverse. And the reason why they do have a voltage reduction, so this, my control circuit, you can see start right here. Here's all my control circuit, and I reduce my 480. Let's just say the system was 480. I drop it down to 120, safer, more or 24 volt. You can reduce it to 24 volt to make it more manageable, safer for the control guys and gals to work on the control side of the circuit. And when it comes to washer guys and 70E, when the control guys come and go to the control side to work on it, if the voltage is 24 volt, they don't need to put the PPE if the power side is isolated. So when it comes to PLCs, it's a lot of advantages of the control circuit being running at 24 volt or 120 volts, so it reduces the PPE rating or gear that you need to put on as you work on this control circuit. And 90% of the problems in any system is a control problem. I mean, the power is easy to troubleshoot, either the power in or out. The fuses is open or blown or not blown. But troubleshooting the control circuit is usually the hardest part. Okay, so that's what you have seen is full voltage, non-reversible, and full voltage, reversible. Now we're getting into reducing the voltage. The only reason you reduce the voltage is to reduce, the only reason this makes a lot of sense is to reduce the mechanical stress because of the starting torque of a motor and the electrical stress because of the high starting current of a motor. Am I missing anything, Dave? Anything else that we use these resistors for? Other than reducing the mechanical and electrical stress by cutting the voltage. So go ahead. Yeah. A what? No. Can you hold, if you can hold your horses, I'm coming to the soft start next. Yeah, it's coming. The soft start is just before the VFDs. You're just ahead of us because everybody loves the soft start now. Okay, this is the old ways of doing business and still used. What they do is they put a resistor. I don't know if you guys can see the resistor in line. So what happens if you have your voltage is 480 here across two lines, right here. As you start your motor, you close these. These will close, and there's a resistor in between. So the voltage that the motor is going to see because of the resistor, say it's 240. So you cut your voltage down to a half or 2/3 momentarily, only for no more than 10 seconds. If you leave the voltage at 240 across the motor that rated for 480, more than 10 seconds, your overload will trip or your motor will burn, right? So keep in mind, we're dealing with this momentarily as in very short amount of time, typically no more than 10 seconds. 10 to 20 seconds, depending on the overload is rated for 20 seconds, but 10-second deal here. And the deal, how do you get the whole timer? Here's a timer here. That's where it times it for 10 seconds here. After 10 seconds, this timer will kick in, close this contact. This will energize. I don't know if you guys can see that. This will energize, and it will shunt these resistors immediately. It will close the second set of contacts, and it will shunt the resistor. Remember, the current always goes through the least resistance, right? So if you put a wire across a resistor, 99.999 of the current will go around that resistor. So what do you do then? Then you apply the full voltage 480 here. Why do we care about applying the full voltage 480 to the motor? Because when the motor starts, you start the motor, no inrush mechanical and electrical stress on the system. After you're up and running, you need to get full advantage of full torque, running torque of that motor to do the process that this motor is doing, like cooling and heating the building. So you have to give it a 480. And if you don't give it 480, you're going to burn it anyway. Any comments, guys, down to the basic? I know these are a few basic stuff. So that's your voltage reduction. Here's another way of voltage reduction. By the way, that resistor that you're looking at can be a reactor. Instead of resistor, you can put a reactor, a coil, and does the same thing. It will cut it. Auto transformer is another common. Auto transformer, instead of cutting through a resistor, you transfer a certain amount of voltages here. The same concept. When you at the start point, you close these contacts, you cut the voltage, and these contacts here, you cut these voltages by say half, 240. And here's a couple of timers here, you by manipulating them. This one, when this times out, it closes this, and the same thing open that one. So it will open all the start contacts after the motor starts and close the run contacts. It isolates the transformer. It doesn't leave the transformer into the system. Unlike the first one, it leaves the resistor always in the system. This one isolates the transformer completely. So that's another across the line. Any comments, guys, about across the line? I've seen them in a lot of application. Cheaper way. The only way if you have a 150 horsepower motor and you need to start that boy across the line, it will screw up your system. So these are 100 horsepower or more, becomes a big deal. Okay, so here's another one. This guy is speed control. This is a speed control where you can have multiple speeds. Now you have to design the motor that works this way. So this has 3. So look at that. There's 16 leads coming out of this motor. When you wire them to a controller like this, and you energize. There is no voltage reduction here. We're not reducing any voltage here. This is across the line speed control. Across the line speed control for motors. So by energizing certain sets of contacts, you can see that arm here. By moving the arm to certain areas, you can close certain you connect and disconnect certain contacts to manipulate the number of poles inside the motor, which give you different speeds. So in this case, I can go forward 60, reverse 60 at 600 RPM, and forward I can go 600, 900, 1200, and 1800 by manipulating the number of poles. That's manipulating the number of poles inside the motor. But your motor have to be designed to be manipulated, right? Otherwise, you cannot use this type of controller. So that's the across the line speed control. But you can see it's not it's a step control. You can't go between 600 and 900. You're either 600 or 900. So it's step control. Any comments, guys, about these across the line control? No? Okay. Moving into I threw wound rotor induction motor. Do you guys use wound rotor induction motor? No? A lot of stuff is induction, right? Full induction. This animal is, there's a lot of types of motor. It is an induction motor, except they have a secondary conductor. It is in the code too. Right in the coil, they have brushes here, you can see, and right in the coil, they tie 6 resistors to multiple contacts, and they can add more resistance in the rotor circuit. The more resistance you add in the rotor circuit, the more you slow the motor. So that motor, my understanding from what I read about it, I didn't specify it, has a good starting torque. Punch presses, they use them. They make short, sudden holes so they have a very good starting torque. They can and you can manipulate the speed by manipulating the secondary conductors, they call them. The secondary conductors is this circuit here. And all this is going to be part of your controller, inside your controller. So you can see that I have speed number 1, I have speed number 2, and I have speed number 3. I have 3 speeds I can get out of these contacts. So if I close if you close the first set of contacts, when all of them are open 1 speed, you close this set of contacts, you got 1 speed, and you close the other set of contacts, you get another speed. So by closing these contacts, are shunting these resistors from the rotor circuit, you can get certain multiple speeds. So what they do is manipulate the current that go through the rotor. That's what that concept. The drawback of these guys, the DC motors, they have a lot of brushes and high maintenance. They have a lot of high maintenance on them. Any comments? I thought just to throw that one because it's kind of unique. Dave, have you guys come across anything that you specified? No, on that one. So we'll move forward on that one. Okay, so I thought just to throw one because special type of induction motor. When we come to three-phase, I threw this one because direction of rotation for three-phase motors. I don't know if you guys get involved in commissioning or being there when they're doing commissioning. When you tie a motor to the three-phase system, you have to identify the rotation of the motor and the phases, phase A, B, and C, that's supposed to go to A, B, and C in the motor, as well as A, B, C goes into the system. If you don't identify them, if you flip them, your motor will go the opposite direction. So there's a phase rotation machine that when they do commissioning, they get into this machine. This machine is supposed to go that way. So you plug it into the machine and you rotate that machine in a direction. It will tell you here if the direction is right or wrong first on the motor. Then you go into the electrical system. You tie it to the electrical system hot, and it will tell you if it's right, ABC, or wrong. If it's wrong, what do? You just flip 2. Anyway, so that's a way of identifying phase A, B, and C when you tie it to the motor. Why? Because if you don't, your motor will run in the opposite direction. Did you come across something like this? Yeah.
Because the contractor did it, right?
Yeah. So that's, I mean...
Usually that's discovered before the commissioning agent shows up when the mechanical guy turns down and the fan on the back, which they figured out.
Yeah. Yeah. But that's what your contractor whom you're working with, or if you guys involved in commissioning with the contractor, these are available machines that they can verify the three-phase. I thought this is a good way to do it. I'm not going to dwell too much on these. Connecting dual voltage three-phase motors. I threw these one just for you guys. Most of the motor are Y motor. This is based my understanding, and I'm not an expert in motors. Most of the motors, induction motors that you're handling is this. Most of the motors are dual voltage, and the reason for this one because they give you say a 50 horsepower motor, 240 and 480. So you can run it at 240 or you can run it at 480. And some of them actually have a whole range of voltages they can run them at. So the way they do them is they make the motor 9 leads. They call it 9 lead motor coming out of that. And if you want to hook up this motor high voltage, you hook him. You're looking at it. So this is, if you hook him high voltage, you hook him this way. And if you want to hook him, this is a Y, that's called my high voltage. And if you want to hook him low voltage, you parallel them. So if this is a 240 and this is a 240 coil, when you hook them together, you get 240, right? Or something similar to this. Or if and the same thing, you see how these are two parallel together. Versus if this is a 240 coil, 240, and it makes a lot of sense on the delta. If this was, say, a 240 here, and this is a 240 here, when you add them, the 240 will get you a 480. So they manipulate the voltages to get you higher voltage and lower voltage, but you have to rehook them. There's also horror stories about people tied a motor to a high, it's connected low voltage and they tie it to a high voltage or vice versa. If you tie a motor that connected low voltage to a high voltage, you burn it, and vice versa. Also, if you tie it to a lower voltage and it's rated for high voltage, you will burn it. So I thought this is just a couple of commonly used connection for the most common induction motors is a Y, delta motors. They use them for high torques. And how to label them? They label them, I don't know, you guys don't get involved too much in labeling. They start from the top coil and they go spiral all the way, and they label them from 1 through 9. So these are called 9-lead motors that you can hook them up high voltage and low voltage. I thought that's interesting at least to know about that one as you deal with the induction motors. Any comments, guys, about the induction motors before we go quick into the DC motor? And we'll, how are we doing with time?
There's one common reduced voltage starting method. The last slide is a wide element. There's a similar to the timer scheme you had for the resistance for auto transformer. You can switch the windings between Y and delta. You start at Y, and after time, contactors open and close, and switch it to delta. And that's another common method of
yeah. You're absolutely right. That's if your motor is a delta. For delta motors, if your motor is a delta motor and you manipulate the starting voltage very easy, you have a delta, a Y delta starter. Start as a Y, rehook them up as a Y. You cut the voltage by 1.73, right? Because the Y It's sitting too close on it. And then when you rehook them again back into the full voltage, absolutely. Okay, so that's for the induction. Moving in very quick, guys, through the DC motor. You don't deal a whole lot of DC motor. DC motor is the same thing, except they have windings in the rotor here, and they have brushes. There are a bunch of brushes that they use. My understanding, and help me, you guys have been in the industry, they use them a lot for speed control in the past. They are awesome for speed control. Or if you want to speed control them, all what you have to do is just cut the voltage. How do you cut the voltage? The easiest is just take a resistor, put it in line, cut the voltage this amount, the speed will go this amount. No frequency to interfere with your system. So that's the advantage of them. And they have good torque too on them. So they make them out of, they call it the series fields, shunt field, and armature, which is the coil inside here. And when they hook them up, and if you want to know the difference between them, I don't want to dwell too much on it, guys. The difference between short shunt connection and long shunt connection, this all have to do with the starting torque capability of the motor. If you want higher starting torque on the motor, you hook it up in a certain way. Lower starting torque motor, you hook it up in another way. So when they're using them for conveyors to carry more loads, the way you hook them up becomes a big deal. So there's a short, they call it short shunt connection, long shunt connection, and you can see the cumulative compound and differential compound all has to do with the starting torque capability of these motors. Okay, so then I thought just to throw these as an example, if you guys came across, without dwelling too much on them. Now, we don't have DC power sources. We do not generate power. Do you guys get from Excel DC? We don't get from Excel DC. So when you have a DC motor, the first thing you need to think about, I need a DC drive, right, to drive that DC motor. So here's a DC drive 3-phase full rectifier. So this will take the power that's coming out of that's your DC drive, the power that's coming out of your system, and convert it via these diodes into an AC. So you're familiar with the full, this is the full rectifier, and it will, when everything is done here, this voltage will look like this with some ripples, and then they put some capacitor to smooth it. You get into the rectification, right? So this is, for all practical reasons, the motor likes this. Yes, a little ripple on it. They smooth it with capacitors, but it looks like a nice DC. Took a 3 AC loads, converted into a DC system. So that's how you run a DC motor these days. A DC drive. You buy a DC drive, bring the power into it, convert it from AC to DC at the right voltage, and run your motors. Any comments, guys, about the DC drive through the rectification process? So here's a DC drive, and also they have the silicon, what do you call these? Controlled silicon rectifiers, is that what they call them, CSRs? Controlled silicon rectifiers. That's, silicon. Did I spell it right? Silicon controller. Yes, that's what I thought. SCR. Flip them. Thought they look. Silicon controlled rectifier. SCR. Yeah, can you guys flip that one? My apology. So what they do, these guys also, they can manipulate. What they do is they cut the voltage, phase shift here electronically. They manipulate the AC voltage by turning them on and off at certain values to get you the effect of the DC effect right here. And what do they do with this? They dump it across your DC motor for your DC motor to run. So you're looking at basically at a DC drive. Any comments, guys? Any questions about DC drives? Which you probably don't specify too much, but that's your DC drive, is always with DC motors. Do we use them? Do you guys use them for anything else on the motors? Is there anything that you need a drive for them? DC motors. So you put a DC drive on them. Okay, now the last one is now go into the solid state electronically. So we have two, so we do across the line mechanically, like with the full voltage non-reversible, and then we mechanically reduce the voltage through a transistor or a transformer, right? Now we can do the same thing. We can reduce the voltage electronically by manipulating the signal, the AC signal that's coming to the system. So solid state reduced voltage, this is equivalent to your auto transformer reduction or your inline resistor, what they call them. And so that one give you one advantage, ramping your motor up, ramping it down to cut on the stress, the mechanical and electrical stress that starting and stopping a motor will impose in your electrical and mechanical system. Do you guys use a lot of these, speed control or solid state reduced voltage? A few of them. So where would you use something like this if speed control is not an issue? If you care less about running this fan at 800 amp and 900 amp, 800 RPM and 900 RPM, you really want to run it at, say, 1750 RPM. Care less about the speed control. But you care about the reducing this mechanical electrical stress in your system. Soft start, so-called soft start will be your baby. Solid state reduced voltage or soft start. Of course, the big buzz in the industry right now is the adjustable speed. Adjustable speed give you what a soft start, solid state soft start will give you. Ramp up the motor, ramp down the motor, and speed control. You can control the speed of your motor, and they come in different. You guys will deal with them all the time with the mechanical engineers. Do you guys do your mechanical specify the VFDs because there is a lot of mechanical characteristics they have to match, or do you guys specify it for the mechanical equipment?
Usually the mechanic specifies it, and that's where we put motor control centers together. And the VFDs are going to the motor control centers and the motor control centers.
Okay, but there's a lot of coordination and talk, because when it comes to speed control of a motor, every time you manipulate the speed of a motor and the voltage with it, so you don't burn the motor, you have to pay attention to the torque, the starting torque, the drop torque. You could manipulate the speed to a point where your motor will stop. So there's a whole lot of characteristics as you manipulate the frequency and the voltage to get your control speed. 6 pulse and I think there's also 12 pulse, wasn't it? There's 6 and I think 12 pulse modulation and 18 pulse modulation. The more you modulate, the more pulses you cut the AC, the smoother the control of your system would be. So 6 pulse would be worse than an 18 pulse would be much better than 6 pulse. Any comments, guys? Any questions about the use of the VFDs and the soft start? The VFDs and soft starts? Comments? Okay, so that's here's a couple of examples. These are courtesy of our friends at Square D. So why do I keep calling them SCRs? Are they SCRs? I should have brought my. Oh yeah, SCR. The other one was CSRs. Okay, that's what I thought. SCR, silicon controlled rectifier. So what they use the silicon controlled rectifier, and they fire them and at certain speed. So the soft start, here's how they do the soft start. The soft start, they cut the voltage. Here's your AC voltage coming really beautifully. What they do is they shunt them, they close these contacts. Now we have 0 voltage coming in. Here's 1 pulse, shunt it again, here's another pulse. So they give these pulsation to the motor as the motor starts. They close them, so they manipulate the frequency at the level of the frequency. See how fast these are to open and close at the level of frequency. So your motor will see pulsation coming into that motor. When these pulsation average mathematically each other, it will average to a reduction in the voltage. And that's where you get your voltage reduction electronically. What happened to your amps? Your amps is a function of your load. If your voltage is connected to your equipment, your amps will go through. So when you have momentarily your voltage went down, so momentarily you reduce your voltage, also your current, your starting current will go down with it. Momentarily. We're talking about only 10 seconds though.
That's a lot of cycles.
Yeah, 10 seconds, no more than 10 seconds. For 10 seconds, you reduce the voltage either mechanically or electronically. By reducing the voltage, the impedance is the same, but you reduce the voltage, or the impedance also, this is high frequency. So you reduce the starting current momentarily. Your torque will be reduced to a level too.
Less power out of it then.
Yes, at the beginning. Yes.
Yeah, then Jeff, obviously those voltage waveforms you guys there, power is an integral of voltage waveform. So in the second waveform, you're taking the integral of that little tiny corner, this very, a tenth of the power of the full thing, and then when you get to the bottom one, you start to have half the power. And so if the power is cut in half, then the current flow essentially is cut in half.
You cut you proportionally almost.
Instantaneously.
Yeah.
Like that.
And that's where when it starts on the start socket, it's like 100 horsepower all at once. It's 50 horsepower.
I just get it in my head that, I times E equal, power, so the voltage goes way down.
But if you times
That's a simplification. Like I said, that look at the area under the curve. The area
Yeah.
under the curve, that's your power.
yeah.
So you can see that the top, the full supply voltage has got full power, and the one in the middle is only a fraction. So the soft start applies a very small fraction of the power for a couple of cycles, and then as the speed gets going, it goes to the third curve. And then when the motor gets close to full speed, it goes to the top curve and applies the whole.
So if you hit these when I was in college, if you multiply this curve by the current here, I, this is a voltage, and you multiply it by the current, you get yourself the voltage, right? So this amount of voltage is, if you add to it this amount of current, what voltage times current is your power. So you are, like we said, this is the amount of power coming into your building. I have to bring, you guys have to bring Jerry to talk about these, because these are their territories in terms of manipulation. Okay, but the concept is really manipulating the voltage. You can see by reducing the voltage, you got yourself soft start for a motor. Ramp your motor up, ramp it down if needed. They do a couple of other functions. Okay, so that's your next step. Any comments, guys, about the soft start? Any comments? Soft start. So that's a second thing that you do. Only needed if you reduce the mechanical and electrical stress on your starting mechanical and electrical stress. The last one, guys, you do is VFDs. VFDs will give you the two advantages. Start your motor at a reduced voltage, reduce the mechanical and electrical stress, and at the same time manipulate the voltage to get you multiple speed. So what they do, the smarter than Chad, they add IGBTs here, the most advanced technology, and they put a couple of chokes and capacitors. So first you reduce the voltage into DC, then you manipulate, so you convert it to DC, then bring it to the drive, and then start firing these DCs at different intervals, opening it to manipulate the voltage. You have a couple of to get you here's a good example. You convert it into DC. You take the AC here, which is weird. You take an AC here, use diodes or CSRs here, convert them into DC, a couple of choke for protection. Then you start inverting them back to AC again. Except the AC that comes out of them, it looks like pulsations. This one using SCRs with the transistors, and these are using the IGBTs, and I believe the IGBT is the most advanced technology. The smoother, the better, and so forth. So your motor will be looking at pulse, and instead of looking at sinusoidal wave coming in here, complete sinusoidal wave, it will be looking at pulsation going into it. And as far as the motor concerned, that's good enough. So, any comments, guys? Any questions?
Actually, the bottom of bipolar junction transistors, see those stuff back because the problem was that it couldn't handle the power.
The bottom ones will handle better power than the
So
IGBTs.
now they increase the power handling capability of bipolar junction transistors, so you can manipulate the waveform better. You can see the IG. It's like a gate.
Give you a better, smoother.
But basically, it's what bipolar junction keep it closer to a oscillating signal.
Okay, so that's kind of the basic function of what goes inside your VFDs, firing them. That process will trick your motor to run at different speed. Manipulate both the frequency by these pulsation as well as the voltage level. Because if we could, in an AC system, if you reduce the frequency only and the voltage stays the same, you will burn your equipment. You have voltage have to go proportionally or so with the frequency. Any comments, guys, about these? Anything else that you want to talk about? So I thought this is just the basic about the VFDs. A couple of things that you can do with them: speed control, low speed torque. There's a couple of things. I mean, you can program them with the current limitation. How much current you want to impose in your system? Voltage per hertz. What's the ramping curve for you? Maximum hertz, maximum speed. Every time you see a hertz on the VFDs, it's a speed. What's your maximum speed? What's your minimum speed? How do you want to ramp from minimum to maximum? Is the curve the slope is this way, that way? So manipulate the slope. And the current limit, I believe, is how much current is starting current you want to allow to get into your system. Of course, acceleration, deceleration of your system, starting your motor, up speed, slowing your motor, call it ramping up and ramping down of your motor. And it has to do a lot with the torque. As you ramp your motor up and down, you want to make sure that you maintain the torque, the starting torque when you ramp it up. So there's a lot of, you guys get involved in programming them, or, you know?
Usually left up to the temperature control program.
Okay.
We don't have
Yeah. So there's a lot of manipulation that you can do there. You can have they can provide an overload protection inside them. You can reverse the three-phase motor inside them through this process. I don't know if you use them to reverse a three-phase motor, guys. You just use them to run, but they are capable of switching certain things with one little switch, and then the motor will go in either direction. So that's your VFDs. With
our mechanical guys, if they wanted to move something from one place to another and then back, they would probably have two separate motors.
two separate motors.
So, that would select forward or backward as opposed to the motor that goes in reverse, because then you run into issues with valves.
I see. So if they want to flow the energy, they use just a different motor to do that.
They would use a separate set of pipes and a separate motor and a separate pump, but they can go back.
Okay. Yeah. So a couple of things I thought to pick with inverters. Inverters create a lot of heat in motors. So the Smarter Than Chad start creating motors with more robust, bigger, stronger, can handle the stress that coming out of. Imagine maintaining the same torque at between, say, 500 RPM all the way to 1800 RPM or even higher, maintaining the same torque if it's constant torque on a machine while manipulating the voltage. So it creates a lot of stress in your system. So what they do is they have, some of them have separate blowers, so they have an inverter rated motors. Do you guys specify them with your mechanical, or the mechanical equipment say inverter rated motors on the mechanical machines? Do you do?
You have to do that on there, like.
They're made by manufacturers. Yeah. Yeah. So that's so it allows it to cool. The idea of the separate blower allows it to cool. Insulating paper in between, so they put a lot of insulating paper in between them. As you insulate them, heat that you are trying to get rid of the heat. So they become phase paper added to the terminals. So as the terminals come out, they added more phase. So we made them differently. Magnetic wire used in the motor windings has a higher rated insulation, the magnetic wire that they wind. And of course, as a result of adding all these paper and all this stuff, your motor becomes slightly bigger. Then an inverter, 15 or a 30 horsepower inverter motor will be bigger than a 30 horsepower non-inverter rated motor. And my understanding from what I read about them is the motors start failing, so the manufacturer, in response to the VFD introduction, start to make their motors more VFD friendly, put it this way, for your equipment. Okay, so that's a couple of things, guys, about I thought operation of motors. Now we have now we got out of the guts of the motor. This is on the left side. You have a beautiful AC windings coming here. I have a 10 amp motor. It's a 10 amp. You can see the overload is sized appropriately, which is 1.25 times 10. That will give you 12.5. And then my fuse is sized also appropriately, which is 175% of the full load amp. That will give you 17.5 amps. So that will, you end up here with a 20 amp fuse, of course, because we don't have 17. So in a case like this, the motor is running 10 amps, overload is sized appropriately, the fuse is sized appropriately, the motor will run forever. On the left side, here's what happened. This one, if you have a short circuit, I'm sorry, an overload. So if you have an overload condition, so how would you have an overload condition? Your machine is overloaded mechanically. So we don't have a whole lot of control on overload. Mechanical, they load it, and conveyor, it's carrying more stuff. When you overload it, if your motor, if your overload, look at that. So I size, if my overload is sized not appropriately, this is a wrong size of overload, then my motor is loaded here 5 amps more than what it can handle, more than the windings can handle. Long story short, what you're going to see is a charted copper wire or magnetic wire inside the stator will be burned as a result of an overload. And these are pictures from manufacturer, guys. So if you open the motor, it looks like this. This is an overload condition. So how do you protect this one? The one on the left, if it reaches 15 amps, overload will open. So it wouldn't burn it. Okay, here's another condition here. Condition, this one here, we have an open phase. Can you guys see that one? So you have an open phase. One phase, we lost phase. Right? Could be a fuse. The utility coming to your building lost a phase. That happened. So you lost one phase. Now when you lose one phase on the whole system, if you look at right here, one in a delta system, the amps will double. I don't know if you guys can see that. I have 5.8 coming in here, will double to get me 17. So one phase, the two phases will almost double their amps to compensate for the loss of the third phase, and your motor, if it's running, will continue to run except to start humming. You probably have seen them guys humming and making a lot of noises. If it's running, if it's not running, it would not start, depending how big the motor is. So now you have 17. If your overload is sized appropriately, 17 amps coming out of 12.5, you have 10. If you're using class 10, you have 10 seconds. This overload will open and protect your motor from open phase. You can see, if you're looking at it, one phase here is burned. So that's an indication that you have an open phase condition. Open phase condition. So these 4 coils are associated with phase A, as they put them in a 4-pole motor. So that's only that phase is burned. So that will indicate that which is the 17 point, this particular coil right here, the one that's going to be burned. So that's an indication over phase. Now if you have a delta, this is a delta. If you have a Y, which is the most common, the same thing, open phase, you can see we lost the amps in one phase. We compensate by adding more amps on the others. So then you can see it's 2 sets of, now it's 2 sets of coils are burned. Because the 2 of them, the 17.3, the 2 phases will be burned, except if your overload is sized appropriately, like it is 12.5, it will open within 10, if it's a class 10 or class 20 or class 30, 10 seconds, 20 seconds, or 30 seconds. So I thought some visual indication of why overload protection motor is a big deal. This is if you have a delta, single phase on, if you have a transformer and you're singling on the primary of the transformer and you have a delta, because of the transformer in between, there will be current here, right? Because the transformer takes all the magnetic energy from the primary, converted to 3 phases. It will be unbalanced though. So you can see that there will, one of these as a result will have a huge amount of current coming out of it. In this case, if you don't have an overload protection, which you should have right in here, that phase will be completely 23 amps going through a coil that's rated for, in this case, 10 amps. You will burn it unless you have an overload, which will trip it at 12.5. Any comments, guys? Any questions about that? So this is just a story that if you have a single phase, a smaller motor, by a bigger motors, and you're single phasing, the bigger motor will create a kickback energy, and that will compensate for the loss of the phase. So if you have a single phase condition in your building, your three phase motor could easily start as long as another bigger 3-phase motors have been running before the open phase condition happened. So anyway, all these are just examples why overload protection is a big deal in a case like this. A lot of motors, guys, and even VFDs, they have loss of phase control, so they can monitor what's going on in the VFD. And the soft start, I believe they also have loss of phase control or protection. Okay, this is an unbalanced voltages. If your voltages NEMA will allow you to have a 10% plus or minus voltage. So if your system is rated for 460, you can go 10% higher, 10% lower. Then and still the motor will work within its specified range. But this is just an example of what happened if you go 10% higher on a motor. Look what happened, the full load current will go up, the starting current will increase, temperature will increase. You can see all this temperature will, so temperature rise at full load will decrease actually because the voltage went up. And the full speed, you can increase your speed slightly. So all these are just giving you an idea what happened. If you reduce the voltage as expected, your full load amp will increase, your starting current will decrease, the temperature will increase now because the temperature will increase, and that will reducing the voltage will contribute to reduction in your full speed. So a couple of examples that I thought the effect of voltage reduction, voltage unbalance into your system. So if you go to a system and you measure the voltage supposed to be 480, you have 485, 480, 475. You take them, average them, and if you are within these ranges, the motor should work. If you're more than 10% from the average, the furthest, then your motor might not, it's not working within its parameters. Any comments, guys, about the unbalanced voltage, which could contribute to eventually the burn of your motors? So I'm going to move into. Okay, so what I know you guys don't like current limited fuses. We talked about this one, but I borrowed these one from the specification guide. So this is a few things when it comes to the motor. What you need to do what do you need to protect when you're dealing with a motor? You need to protect your motor starter, that be a VFDs or the coil of the magnetic starter. The overload itself needs some type of protection from a short circuit. Motor damage, the most important thing is we want to protect the damage curve. I don't know if you guys can see it right here. That damage curve, that's if the current reached that point, the motor will start smoking basically. Then your conductors, you need to protect them. Thermal withstand limit for your contactors, I believe. Contactor breaking current, contactor withstand, MCCP, the circuit breaker. This is your circuit breaker that's protecting the system. So all these giving you an idea again of what type of level of protection you have. If you look at the level 2, no level 2. Level 2 will tell you, we talked about type 1 and type 2 protection. Type 2 protection, type 1 will protect you and will have minimum damage to the equipment, but the equipment might not function, might not work. Type 1. Type 2, when you have a short circuit condition or ground fault condition, you basically flip the switch and everything is up and running. It's safe for you and safe for the equipment. That's type 2 protection. To achieve type 2 protection, you're supposed to use almost current limiting fuses to achieve that one. So single phases, this will protect you. So that's, I don't know if you guys can see the overcurrent protection device sitting right in here. It's my overload is the blue. So between the overload curve and the overcurrent protection device, I have basically good protection with molded case circuit breaker here. That's rated at 250. And my curve here, the motor damage curve, if your overload here is not to trip, is say to malfunction, you are alone. Your motor will burn. If your overload is to malfunction, you don't have to backup plan what happened if your motor is malfunction. If you look at this one here, this will give you type 2 protection. I don't know if you guys can see the fuse here. Right here, the fuse, right at the top here, will act as a backup overload for your system between the fuse and the overload. So you have the overload, the blue, will protect your system from overloading, and then whatever color is that will, if it doesn't work, it will act as a backup for overload. The green is the starting curve. You are familiar with the coordination. Your fuse or your circuit breaker should allow the motor to start right here. If it goes higher than that in this level, it will open and it will be seen as a short circuit or a ground fault. So you have a type 2 protection. It protects you from single phasing because single phasing will be seen as an overload. Backup single phasing by the fuse. Overload protection backup. Overload protection. backup for your system, and it will also protect your conductors or your motors. So supposedly, that again, current limited fuses will provide you a full type 2 protection for your equipment. Any comments, guys, about these curves? Any comments? Any questions? So I picked one that's fuse, and this is directly from the SPDs here. One that the fuse, and one for the circuit breaker. Just to be fair for the circuit breaker, guys, look how high they're sizing the circuit breaker to 50. If you guys have SKM and you have an adjustable circuit, an instantaneous adjustable circuit breaker, you can size the circuit breaker as low as 125% of the full load current, and your motor will still current, as long as you have adjustable circuit breaker. And I have an example for you. So really, this one, if you have the adjustable circuit breaker, look at this here, that bottom, where am I here? Right here. If you can adjust this and you can bring it down here, that will reduce your arc flash, arc blast inside your building, provide very, very good protection because you're close to the motor. So your motor could a much better protection. So you can bring the whole curve down if you have adjustable instantaneous circuit breaker. Any comments, guys, about these two types, type 1 and type 2? I picked for you, especially when it comes, the reason why it becomes a big deal for motors, because motors are very equipment. There's a lot of control involved in them, and the machines themselves are very very, very expensive machines to deal with. Comments, questions about class 2 and class 1 and class 2, or type 1 and type 2 protection? So that's kind of what I wanted to do. That second thing, I want to walk you guys very quick through the NEC code book. The NEC code book, this is directly from the NEC code book. It says if you have a feeder, you have to provide an overcurrent protection device right here for your feeder. That's your fuse at the feeder that feeds multiple motors, and then right underneath it, and these are the sections from the article that talks about it. Then underneath it, you have to have a disconnect for your branch circuit disconnect, so you can safely isolate the system, the air handling unit. You can work on it safely. That's OSHA enforced. Then you have to have an overcurrent protection device, a second overcurrent protection device. That's for the branch circuit. Now we brought the power directly to the motor, except we need to be able to control that motor, so we have to have a controller circuit, right? Controller and controller circuits that goes into it. The VFDs, magnetic starter. And then you have to have the overload. We know what we have to overload. The overload will protect your windings upon the existence of single phasing or overloading of the system. Then you have the motor itself, and some motor have something called thermal protection. I don't know if you guys deal with them. Bigger motors, like 1500 horsepower motors and 3000 horsepower motors, they have embedded resistance in them, and they basically have sensors in the guts of the motor. They can have an image, a thermal image of everything that goes into the guts of that big motor. They use them in 3-phase motors. Do you guys deal with them, Dave? Any of these? So these are high voltage motors. All of them, they have sensors embedded in the windings, and they tell you what the temperature inside the guts of that motor before it starts burning. Why? Because they're so expensive. Smaller motors that we use in air handling unit and chillers and so forth typically don't have them. Then you have the secondary controller, conductor, and resistor. You guys remember the secondary controller and secondary resistors for the wound rotor motor? That's exactly what they're talking about. If you have a wound rotor motor, you have resistors on the secondary side tied to the rotor. So that's what the kind of the layout of the NEC. Any comments, guys, about these from the NEC? Moving away a little bit from it. When we have when you have an MCC, or if you have a feeder with a gutter and you're tapping it, either way you have to provide two types of protection. And I have examples for you guys. I gave you 4 examples. 3 of them, I believe, are single phase, a 3-phase induction motor, and 1 DC for calculating all this stuff. So the code requires you to protect first the branch circuit, and you can see here's my branch circuit, including the contactor, the overload, as well as the motor, as well as the conductors. All these have to be protected from short circuit and ground fault, right? And then you can see 2 branch circuit, and at the same time the feeder, I don't know if you guys can see right in here, this is my MCC that I need to protect it. 600 amp circuit breaker, in this case, or fuse, will be protecting the feeder that's bringing the power to the MCC, the 600 amp MCC, the MCC bus itself, and the line side of all the fuses. You can see the line side of all the fuses will be protected by so-called the feeder. Any comments, guys, about protecting the feeder that feeds an MCC, and from the MCC motor control center you feed multiple motors? That's the rich man's way of doing business. The poor man's way of doing business is you have a gutter on the wall, gutter, and you bring a feeder, 500 kcm feeder, and you tap with lugs, and you feed all these motors from them, and you put the starter and the disconnect right on the wall. Do you guys do that? You're a group, you're engineers too, probably. Either way would work. The MCC is more, of course, gives you a lot of advantages control-wise and so forth. So I thought that's and okay, then we move into the, so we know for motors you have to have the overcurrent protection device here, you have to have the overload, you have to have the controller. What we're not showing here is also a disconnect, typically right next to the equipment you need a disconnect. And the function of the fuse, guys, is to protect them from short circuit and ground fault. The function of the cable, the branch circuit, to bring the power to the motor. The function of the controller to start, stop the motor, ramp it up, ramp it down, and speed control it if needed. The function of the overload is if you overload your motor or you single phase it, it will protect your windings from burning because they're a very sensitive piece of equipment. So all these, and the last one is the disconnect. The function of the disconnect from OSHA and 70E, we talked about it, guys. The rule is you energize, you put the equipment in a safe working condition before you work on the equipment. You need to lock out, tag out. To lock out, tag out procedure, the rule is your disconnect have to be within sight of the controller, the motor, and the driven machine. Because you could have a machine sitting there and the motor is sitting here driving that machine, and your fingers could be lost right there, not here, right? Everybody know, I always say we have the disconnect because people kept putting their hands into machines and their hand stays there. You know, and somebody flipped the switch. Can you imagine what happened? So that's the whole idea of having a disconnect. The reason for the disconnect is safety. As you isolate the system, lock it, tag it, work on it, energize. So the rule is you have to have him within sight of all of them. If you can't, then you have to have, I don't know, you have to have two. One will be within sight of a controller and one with sight of the motor and the driven machine. So that's the rule. The rule. Now the exception that we can do is, here's the exception where you can have a one disconnect in one location. Not when we say within, everybody knows what within sight is 50 feet. Within sight is 50 feet. No longer than 50 feet, no obstacles in between. I can see it, it's not further than 50 feet. This is an exception for not within sight. But look at where the exception is. Here's where the condition is. Number one is you have to have individual. You don't have an individuals, but a disconnect impractical. Do you guys take advantage of this? Putting the disconnect in one location would be impractical. I don't know how you're going to define that. Impractical, or might increase other hazard. So you have an air handling unit and you really don't want somebody to go flip the air handling unit, shut it down because you could explode, or the process that machine is doing is very chemicals or so forth. It creates more hazard if you shut it down while energized. So then you put it somewhere so that's the exception, again, the exception. Or if you are in an industrial installation and you have a safety program for your people to work, and you have a bunch of very smart, qualified, well-paid, well-compensated electricians who love you so dear, qualified people, then you can put your disconnects anywhere you want. Other than these two, your disconnects must be within sight of the controller, the driven machine, and the motor, or you have to have multiple of them. Do you guys encounter the exceptions here, or you always use the rule?
We do, like, we better have a darn good reason for not bending over backwards to get a disconnect within sight.
Yeah. And it, so that's
industrial installation, you know, those, even those, we just did the paper mill and exactly, and they still want the district. They go way out of their way to not spend money, but then they want the disconnect because it's safe. So the room is draining down water coming out of the logs, and they still, so they have water with disconnects, they still want it.
for safety. Yeah. And when we talk about electrical machines, guys, I mean, this could be a chiller, and the people who maintain it have nothing to do with electricity. They're mechanical contractors. They know a few to be dangerous. So it's not just locking it for the electricians to work on it. All the mechanical trades will be working with these machines. We're not just talking about the motor, we're talking about the machine that motor is doing. So locking it, not for just electricians, for anyone who's to work on this machine.
I think it's worth pointing out that if you went back 4 or 5 codes ago, the wording was different, and it said that you could have a disconnect located otherwise as long as it was locked out.
Cable locked in open position.
A long time ago.
Yeah.
So now the lockout is over that.
And that also went with the 70E. The 70E is becoming more stringent in working on de-energizing object, locking it, tagging it, make it easier to lock it and tag it too. Okay, so I am motor installation 3-phase. I just grabbed this one from SPD. For motor installation, guys, you do the calculation. I gave you the examples, or if you're like Chad, don't like to do calculation, Color Hammer has a list on there. You have the engineering specifier for Color Hammer. I don't know if you guys use it. Square D has the same thing, has multiple tables that you can, a 15 horsepower motor that running at 208 and 480, they give you the conductor size, the disconnect size, the conduit that goes with it, everything. Color Hammer and Square D. Also, this little booklet have summary of all these. If you have a 100 horsepower motor, it will tell you what type of NEMA do you need for it. NEMA, starter, magnetic starter, no VFDs though. What type of disconnect you need, what size of disconnect you need, what size of conductor you need, and what size of conduit EMT that you need for that particular motor. So you don't have to do the calculation, because these are standard, guys. And even the overload, some of them put you the overload based on the 2 conditions, 125, 115 and 125. This is one coming from SPD, using fuses only. Square D uses, and Color Hammer uses a lot of circuit breakers, so they tell you this circuit breaker, and I looked at their circuit breakers are size slightly less than what the NEC code book say, the circuit breakers, because they want to lock you into the circuit breaker that they use, their own circuit breakers. Okay, so that's what I thought, guys. Just walk you through. I hope it wasn't too simple. Any comments, guys? Any questions before we move into a few things in the NEC code book? We have half an hour left. I kept you for the most part awake, huh? That's good. So I do, before I go ahead, and I'm going to go directly to the NEC code book. You guys, if you have not highlighted these, probably I always say go ahead and highlight it. I have all the references for you in the sheets that I gave you, not like you guys don't know them. You know them because you define them. So I'm going to go to the NEC code book and probably just make sure that I highlight a few tables. Here's a table, very important table. The locked rotor current of a motor. That's the starting current of a motor. If you're doing some calculation and you want to put in SKM, the locked rotor current of the motor, these are also in SKM. So if your motor is a design B, the locked rotor current is 3.5. You go the upper limit because that's the worst scenario. So that'll be, for B will be 3.54 multiplied by the horsepower, multiplied by 1,000, because that values are given in K, and then you divide it by the voltage if it's single phase, or if it's 3-phase, you modify the voltage by 1.73 because 3-phase. That's how you find the starting current, locked rotor current for any AC machine. So I thought that's really interesting for you guys, just to know that this table exists. A couple of, here's your direct motor rectifier supply. They changed them in 2000. How do you size? So how do you size? You have a DC drive, and how do you size the conductor going to the DC drive? No problem. You take the input of that drive and multiply it by 1.25, and that's how you size your conductor. So a couple of, I thought, really interesting in the DC drives and so forth. Here's your Y-Star Delta Run motors. There's a few things here. I don't think you guys got involved too much into the change that happened in that one. We have 20. Did we pass the overload? Continuous duty motors, continuous multi motors. So I'm going to go continuous duty motors, 1 horsepower. Okay, so here's the overload right here. That's what I'm looking for. So continuous duty motors, 1 horsepower, separate overload, which is typically we use. This is in page, that will be page 319, the top right of 319. These are your multipliers for sizing the overload. If your motor is not, service factor is 115, it says service factor 115, or 125 or larger, you take your full load amp on the nameplate and increase it to 25%. So if it's a 100 amp motor, full load amp, your overload can be set as high as 125 amp. That will protect you from single phasing and overloading your motor. Now, if you're also temperature rise, if the motor says temperature rise is 40 or less, it has to do with the construction of the motor, then you can also use 25% extra when you size your overload. If it doesn't say anything, all other motors is 150. So these are a big deal when we size overload. I don't know if you guys get involved in sizing overload. Typically, the contractors, they go tweak it, but it's good. I mean, it's if you're advising a customers, because we're going to maintain this system, it's good to look at them if they're sized appropriately. So that's the most common thing for the overload. And with some into the most common things. Here's this table. If you don't, I'm sure you guys know this table. These are how you size the fuse and the circuit breakers. There are 4 types of overcurrent protection devices that you can put on a motor. One is called non-time delay fuse. What you see is what you get. You see a short circuit, bam, it opens so fast. Dual element time delay fuse. This is, they inject a little bit of delay in it to allow the motor to start. So you can see if you're using for a motor 3-phase, if you're using non-time delay fuse, if your motor is 100 amp, your fuse have to be 300. If you use a dual element time delay fuse, you go from 300 amp fuse down to 175. Well, that's almost half. So to give you an idea what you when you specify the right. So if you have a motor and you're using a fuse, dual element time delay fuse is your fuse of choice. So these are the 2. Then circuit breaker wise, you have 2 options. Number 1 is inverse time circuit breaker. That's the thermomagnetic or electronic circuit breakers that we deal with. So if your motor is 100 amp, 250 amp is the largest setting that you can do. If you have SPM, you do not need to go as high as 250. You can actually tweak it down as low as you can, especially if you know what the type of motor and the starting torque, and so you don't have to go 250 amp to the max. I don't know if you guys do have a rule of thumb. Will you go always to the max?
175% is a pretty good number
For all.
for inverse time breakers.
Okay.
Normal motors that will not trip as a nuisance, but doesn't drive you up to.
You don't go all the way up. Yeah. So the 2 things when you go as high as the code allows you. Number 1 is equipment becomes very expensive, because 250 circuit breaker might be more expensive than 175, and it might not fit in the panel that you have. There are certain panels might not fit, so you get into the whole fitting circuit breakers if you're remodeling, especially remodeling. And number 2, the lower the circuit breaker, the more protection, arc flash protection you will have, as well as short circuit protection. The higher the setting of the overcurrent protection device, the less protection from arc flash, arc blast, as well as short circuit. So lower is always better when it comes to the overcurrent protection device setting. But what the problem is, you set it too low, it starts tripping and causing a lot of nuisance tripping. Okay, inverse type instantaneous strip circuit breakers. These are magnetic only circuit breakers, special. They look exactly like any circuit breakers, and they size them based on the short circuit that they're going to carry. They're going to pick up at 800. These are not a full load amp. In this case, 800. When it says 800, it dials to A. A will say 800. It will start picking up at 800. So these are not. Do you specify them? I think Hammer called them motor controller protector or something like this. They look like a circuit breaker, except when they build them, circuit breakers thermomagnetic have 2 components: one thermal, one magnetic. So they take the thermal, throw it out the window, and they keep the magnetic component. So what's the advantage of it? Cheaper, because what's the disadvantage? Now you don't have a backup for your overload. You don't have an overload backup because it's just magnetic, looking at short circuit the ground fault. So that's a couple of stuff that I wanted to do. Maximum inverse separate protection. You guys don't get into too much into the controller. I'm going to go all the way to the tables, guys, at the end. So there's a lot of few things, but I'm going to go to the tables. Here you go. When it comes to the NDC code book, there's a bunch of tables, very, very important. This is for the DC. There are 2 full load amps for every motor. One is the full load amp on a nameplate. We use it for voltage drop calculation, and we use it for sizing overload. Other than for voltage drop calculation and overload, you will use the nameplate, the full load amp that's coming from the NDC code book for safety. There's safety caution in it, and because we really don't know manufacturer of motors, the full load current will be within certain range. So, right, is that what they came up with? The common denominator between all the manufacturers of the motors, and they say, here's a value you can use, safe for everybody. Here's your DC. I'm going to go directly to, you guys don't do a lot of DCs. Here's the AC single phase. Do you, four phase, two phase, four wire, two phase, nobody uses it anymore. The most common table that you guys are going to be using is this one. I always like to throw an example, like just to be, here's your three phase. Say if you have half a horse, well, half is not a big deal. If you have 7.5 horsepower motor running it at 200, I don't know, have you seen a 200 volt system? There's one in, I think in St. Paul, they're running at 200, not 208. So most likely you're going to be right in here. The 208 will give you 24.2 amps. If you up the voltage to 230, look what happened to the current. It goes down, right, to 220. Now you double the voltage. What happened to the current? Cut by half. You also increase the voltage. It cuts also almost, it lowers it. So that will give you, just looking at it, what's the advantage of running equipment at a higher voltage? Lower amps, smaller conductor, smaller, and less losses in the system, voltage drop and so forth, right? That's the advantage. You can look at any of these. If you have the advantage of any building, 480, if you have the choice of putting any voltage in any building, probably you'd go 480. But what the disadvantage of 480, of course, you have to have a transformer that bring it down to what? 208, 120 to burn your receptacles. So there's kind of a balance. I heard the 15,000 square foot or more kind of cutoff, 15,000 or higher if it's just a commercial office building, 480 servers. Less than 15,000, you can go 208, 120. Do you guys have a cutoff for whatever that you specify? I'm just curious.
Well, it's 150 kVA load.
Oh, depending about the actual size. So the higher the voltage, always the better the system. I don't know if anybody on this side, guys, there's synchronous motors here. These are my synchronous motors, if you specify them. But I always bring to the attention, look at this. These values are given for 100% power factor. If your power factor is 90 and 80, you're supposed to increase these values by 1.2 and 1.25 before you use them, if you ever use these values. Because in synchronous motor, given 100% power factor. These are only for the synchronous motor, so don't get confused. And they give you a range of voltages. So from the voltage is 220 all the way to 240, you're going to be used 230 values. So if you have a motor running at 230 coming from Europe at 230, you can use the 230 value here. Anywhere, any voltages that you get between these two values, 230. Between 440 all the way to 480, your voltage is going to be 460. So they allow you, the manufacturer rate the equipment at a lower voltage because of voltage drop. You can throw it somewhere else. And as far as the equipment concerned, you can go, your system is 480 and you can go pull your feeder and reach all the way to 460, and this equipment still functioning based on the specification if it's rated voltage of 460. So that's one nice one. The other one, I don't know if you guys use this one. This will help you size if you are in a situation where you want to size the horsepower rating of a disconnect. Well, it's easy. The horsepower rating, if you have a 100 horsepower motor, the disconnect have to be rated for 100 horsepower. Now, if you have a functionally associated, multiple motors functionally associated, meaning an assembly line, and you need to have, the code allow you to have one disconnect, because if you shut them down, the process will be shut down. If you have multiple motors driving a machine, you can shut them down from one disconnect, because the outcome, it doesn't matter if one of them is shut down, will shut the machine, or 5 of them shut down. So you can put them all in one machine. So how do you size this disconnect then? In a case like this, that's what becomes very helpful. Then you take the full load current, depending upon, like if you're 480 here, you take the full load current of all these the motors, add them up, and then go down, see if they all add up into this number here, and you go across and you rate your horsepower motor to 200 horsepower. So it allows you to have one single disconnect for multiple motors fit from one branch circuit to one feeder. If their branch circuit typically function associated, they're driving a machine. You wouldn't do that to 5 air handling units. Put them in one branch circuit. So that's what I thought we will go over. Okay, so let me start with one of these. Sheet number 1. Okay, so I'm just going to go quick, guys, over the stuff that I gave you. I'm going to start with one that's 480 because that's the most common. I believe it's number 3. So okay, if you guys go to the sheet that says WS003, that's a system motor calculations, 3-phase 480 induction. The most common motor is the induction motor. So what I thought is, I have this is generated, this one line diagram is generated from SKM. So here's my feeder disconnect right at the top here, and I have a feeder overcome detection device. I call the feeder disconnect 09 just for numbering purposes. 08 is feeder overcome detection device. You go down into the feeder 07 feeder. That feeder could be landing on an MCC or could landing in a gutter that you're tapping, doesn't matter. Then you go tab into, you have your fuse disconnect, so you need to size the disconnect to isolate this machine. The overcome detection device is 05 to protect this machine. Motor 1. Controller, that could be, these are magnetic starters, not VFDs, and then overload underneath it and branch circuit that pulls it all the way. So if you have an MCC, that's typically an MCC scenario. You bring the feeder to the MCC and you pull these 4 motors fed from 3 motors fed from 3 different branch circuits. Any comments, guys, about the riser on the upper left, upper right corner? Now, right next to it is the nameplate values about this motor. These motors are all coming from induction motors. They're all powered from a 480 3-phase 60 hertz. All the terminals are rated for 75 degrees Celsius. We're using a THH conductor because that's important in terms of what we're sizing. And all of them are running continuously. And the nameplate shows motor 1, 2, 3, the voltages that are rated for, the horsepower size, the full load amp, the service factor, the temperature rise, and the code letter. The code letter PCD, which will decide the inrush of this motor. The reason why I group them together is because you need to do kind of the calculation. So these are your code letter. So then if you go right through at the bottom here, the first thing we need to go is to go to table 430.250 and find the full load amp or full load current from the NEC. These are numbers are coming directly from the NEC table. And I'm sure you guys probably have a list of tables that can get you all these calculations in one. But just I thought I put the process here, and I hope if you find any mistakes, please, there's a lot of number crunching here. So if you find it, bring it to my attention or correct it for yourself. So this is how you size the full load. So this is my amps from the NEC code book, right? This is number 1. Number 1.1 I call it, which is, we're still talking about the motors here. The one is coming from related directly to these motors right here. Is the locked rotor current, LRC, locked rotor current. To calculate it, you take the values from table 430.7b, we looked at it, multiplied by the horsepower, multiplied by 1,000, divided by the voltage and the 3-phase modifier. You can see a motor of 65 full load amp will have a 213 amp locked rotor current if it's code letter B. If it's code letter B. This will help us define the inrush in SKM software. These are all can be important in SKM software, and it will define where the inrush starts and ends, or where it ends. Okay, any comments, guys, about 1 and 1.1, the full load current and locked rotor current? Right underneath it, the branch circuit, PC's branch circuit conductors. Motors are continuous load, so you multiply it by 1.25, it gets you 83.3. You go to 310.15B16, 310.15B16, and you size your conductor, a nice conductor that's for number 4. Again, all these are in 430.22. Then don't forget that you have to size the conductor from 310.15B16 under 75-degree column because it says the logs are rated for 75. Does that make sense with that one? Then right underneath the equipment grounding conductor. For most of motors, guys, you end up with EMT coming to the disconnect next to it, and then you flex into the motor because of vibration, right? As you flex, the code does not allow you to use flex as an equipment ground conductor. So you're going to end up sizing an equipment ground conductor that at least can go from the disconnect in the wall all the way down to your equipment if you're tying to an equipment, unless you're coming directly to the machine with an EMT. 6 feet for a fixture whip. Yeah. Now when you're talking about rotating machines, a machine that vibrates, flex 0. It's not qualified because it vibrates and moves. Fixture whip, you're absolutely right. So then you end up, do you guys size an equivalent ground conductor with your feeders going to the motors, or you use EMT as an equivalent ground conductor? Grounding conductor. So that's safer, and even if you have an EMT. So here's your number 6. You size your MT based on the overcurrent detection device, which is right in here, number 5. 125, 150, 175. Based on 250.122 for grounding, it gets you these sizes of conductors. Typically, they are THHN, hold in the same conduit. So I have 3 conductors, 3 for the 3-phase and 1 conductor for the ground. Right underneath them, guys, 2.2, I call it branch circuit EMT. I need an EMT conduit to carry them. So here's how you do the calculation. These are where the tedious becomes. You guys do it by hand, or you have a list of feeders that tells you if this, use this in terms of size of the conduits, or you leave it. We don't leave it to the contractor if it's a major equipment. We size it. So you can do it here, or you can use the calculator, this calculator, and it can get you all the sizes on a spot. And I tried that baby, and it works really good. It comes really handy for especially for conductors at different size, because you have to do the actual math. So here's the actual math: 3 times the cross-sectional area here of the number 4 plus 1 because of the cross-sectional area of number 6. Add them up, and you're going to go to chapter 9, table 4 and table 5. You get this information. That will end up with 1 inch, 1 conduit, and another 1 inch here, and a third 1 inch. Each one of them is going to have 1 inch based on this calculation. I hope I didn't do a math wrong here. Okay, so that's if it's EMT. As you flex it, you bring the EMT to the disconnect. If you decided to come to flex it, which a lot of time we do unless we're coming to the machine, then you have to size the flexible metallic conduit. Same thing. We came up with the same size flex. But you're going to go to a different table when you're looking at the flex, right? You guys did all this calculation, right? From school. The engineer. 2.2. Yeah. Same value. That's why. So again, any mistakes, I apologize, but I'm interested more in that. There's a lot of number crunching. So the process is finding the cross-section area of the numbers and adding them up. Yeah, it sounds like they're all the same size here. So please check these one, guys. Yeah, 0.0973 and 0.0943 3 and 4. That cannot. These two numbers have to be different. You're absolutely right. It's easy to figure out. I must have copied them. Accept my apology. The second, but you guys, you see what the process is. Then you get into the flex the same way. Then I'm going to go down to the overload. Here's my overload. The overload, when you size the overload, there are 2 factors for overload. There's a service factor. So you're looking at service factor and the temperature rise. Service factor, temperature rise. If any one of them is 40 or less, or 15 or more, you can use 115. So 125. So if you look at the overload here, this one is 115. Because the service factor for the first one is 1 and the temperature rise is 50. So none of them meet the criteria of 40 or less or 115 or more. So I use the multiplier of the overload, 1.15 times the full load amp. The full load amp here is coming from the nameplate right here. Okay, so that's your size, your overload here for each one of them, and the overload stays the same. Then you go tweak these overloads slightly to get you the electronic overload to as close to these numbers as you can, but you can't exceed them though. Any comments, guys, about sizing the overload? So 2 of them will be sized based on 1.25 because they meet the criteria of 40 temperature rise degrees or less, or 115 or more. The third one does not meet that criteria, then it has to be sized at 150. Controller. When you go to the controller, these are NEMA type controllers. We size them based on 2 factors: the horsepower that they're going to interrupt, as well as the voltage. So the first one is 50 horsepower, 480 will get you NEMA 3. I hope these are right. 60 and 75 will get you both of them NEMA 4 and NEMA 4. Where would you get these NEMA sizes, guys? Color Hammer has them, Square D has them, or this book has them. I get them typically from that little booklet. Do you guys have a table that size them somehow? If you you size them. Okay.
I have done it.
Well, we go by the color.
Yeah. Sizing the control of its NEMA. Then I have the overcomputation device. I decided to use dual element time delay fuse. These are DETD, dual element time delay fuse, the 175. And then if it's not a standard, if you can't go 114, you can't find a fuse 114. Your Cooper busmen are more than willing to take one of your arms and legs and design one for you. But the codes say if you can't find them, just go up. No problem. Again, as engineers, guys, if you have a short circuit calculation and overcomputation device coordination here, you can easily go down. You do not need to go up. Up is covering your bottom type of design when you go up, right? What the code allows me to go up. So that's basically the max. It doesn't have to be 125. Same thing for all of them. Right underneath is sizing the disconnect. The disconnect, guys, from 430.110a, you can see all the references on the last column, tells you size your disconnect based on 115. Take 115 times 65, give you 75. Your disconnect is 100. Where would you find the size of your disconnect again? DeWalt has the size of a disconnect up to 800, I think, 800 amp. So here's the sizes of my disconnect: 100 amp, 100 amp, 100 amp, 100 amp, and this is 200. And of course, these are the amp size. They have to be also rated for horsepower sizes, which is easy. The horsepower will be 200 amp, 75. 100 amp will be rated for 60, and the other 100 amp will be rated for 50 horsepower. Any question, guys, down to number 6, the disconnect? See the calculation? And I hope this is a review for all of you. I'm sure you guys have done it in the past. I will be kind of jogging memories here. Number 7 is feeder conductors. Now we're going to move. Now we size everything for this system. We need to go up to the feeder that bringing the power to the system. So my feeder, here's how they do the feeder. You take the largest, fattest, fluffiest motor and multiply it by 1.25. And then you add the full load current to the rest of it, and that will get you 261, and that will give you 3 conductors, 300 kcm. With motors, the green ones, guys, we do not pull a neutral. When I was green, I always pull a 4-wire neutral. The advantage of 3-phase machines is you do not need a neutral, so you're wasting your time with another wire. So 3-wire. Where does it tell you to do this? 430.24. I always like, anybody can do anything, but you need a reference for you as you do things. These will give you the references. Okay, now right underneath it, I need an equipment grounding conductor, EGC. That will be based on the overcomputation device for the whole system. So let me here's my number 8. I'm jumped directly to number 8. My feeder overcomputation device, the code says you take the largest fuse among all the motors in your MCC or your gutter, and the largest fuse, that's the 175, add the full load current of the other equipment sharing the same feeder. You come up with the value. If it's not a standard fuse or circuit breaker, drop down to the lower standard, to a 1 step below. So here's my 37. I go down to the next standard, down, not up, and that will be 300. The reason why we go down on the feeder, because we already went up on the branch circuits, right? So you don't want to go up again. The up means a higher overcomputation value, less protection you have. So that's my fuse for the feeder. I can use my fuse then from table 250.122 and come up with an equipment grounding conductor number 3. Then I size my EMT conduit. You can see my EMT conduit. If I use the number right, give me a 2.5. What size did we come up with? 1 here, 2.5. Doesn't sound right? 2.5. And then I go down into the feeder amp disconnect and the feeder disconnect horsepower. So I size my overcomputation device. I size my feeder EMT. The reason why I did not throw an example of flexible metallic conduit for the feeder, guys, would you flex the feeder? You can, but typically if it's a feeder, it's EMT. The branch circuit at the end, most likely you end up flexing it as you tie it to the equipment. So no flex here. You can if you want to do. The feeder disconnect. Now, The only reason why we size a disconnect for a feeder, if we don't want to put a disconnect for each one of these machines because they're functionally associated. They're running one process, so you can disconnect them from one disconnect. That's the only time that makes sense. Then the way you do it, you take all the full load current of all of them, guys, multiply it by 115, and then go to the next standard amp-wise disconnect. Where would you find these? DeWalt has them. That's the amp-wise size. Then the horsepower, add the full load current of all of them from the table. This is 430.25 251B, and from 430.250. First add the full load amps, go size them from table 430.250, that's size 1. Then size the starting current, these are the starting current, add them up, and go from table 430.251B, find the size, and pick the one that give you the largest horsepower motor. So we do two calculations. One based on the full load current added, and the other one is based on the starting current added. And we use two tables to find them. So that's basically it. All of them are the same, the other calculation. Any comments, guys? Any questions about that? Comments, questions? I have 7 minutes to show you SKM coordination for this. Only 7 minutes. Any comments, guys? Any questions about that? So most of the people, guys, will have I mean, if you are sizing a building the way I'm doing it right now in a real life, you're wasting, I think, wasting a lot of time. So typically people have a feeder schedule, size based on these, and other. There's one thing here is not included, is voltage drop. Now you size your feeder, what happens if your feeder might be larger because of voltage drop issues? So a lot of people end up sizing one size up, have a schedule, and move on because of voltage drop issues. Okay, so that's, and the rest of them, guys, are the same. All of them, I have 4 of them. The 4th one, I believe it's a DC. So I'm going to go directly, you guys will have enough time because of lack of time here. I'm going to go directly to my SKM. Here's my SKM. What I did, I took these 3 motors, the 50 amp, the example that I showed you right now, that example, we went through. I have the 50, the 60 horsepower, and the 75, model it, and I added it to what I already existing one-line diagram that I gave you guys, just to give me a value. And what I did, I added an overload to it, controller VFD here, and this one is a NEMA across the line, and this one is a soft start. And these are, SKM can pick these values from the library for you. And if you can model these and give you the damage curve for each one of these components, and you can tell if you are protecting them or not. I didn't go that far though to get these. So if you go to this one, it will refer you to where I'm clicking on the horsepower here, VFD. Okay, so I think so. Should be able to get you into the library, and you get from here. Why can't I get? Oh, here's the information that you can get about this particular motor, the kVA for this particular VFD's rating, and these are a couple of information you might have to model, the reactor and so forth, if any. Okay, when you put this system together, what I'm interested, mainly, let me just delete, is going to the curves, and I have a curve, the first motor. Here's the curve, the first motor for curve for the first motor. So I thought, here's a fuse. I'm going to go directly to the settings. This fuse, do you remember what was the size that we added to? Was 125, right? For the first motor, the 50 horsepower motor was 125. Look at the 125. That's size based on the NEC code book. Here's my overload. My overload is 115. 115. Look, I size my overload is 115. You can see between the overload and the motor you have good protection. But now if you're doing coordination, look what happened. The NEC code book, this is my favorite. The NEC code book say you have to go all the way up to 125. That's the maximum. But if you go down to, this is a 480 system, so I'm going to go down to 100 and redraw. I can go down to 100 and I have full coordination, right? And I drop the, not 125, I will drop it all the way to 100 and I still have full coordination. Here's my starting curve perfectly, right? My motor will be able to start. I can move the instantaneous. I can adjust the instantaneous. You want this instantaneous to be as close to the start curve as you can. So this is perfect. My motor will come up to speed within 10 seconds start. If it stalls for any reason, this will kick in 10 seconds. This guy will pick it up because that's your overload. Will pick a stall and pick it up. If this doesn't pick it up, the motor will see it as a short circuit or ground fault. So you can see how if you have an SKM and you know, of course, this is an HKD type Cutler hammer circuit breaker. So it's specific. If it's a QP or somebody else, you have to do the same thing on it. So my point is, you can easily go much lower than what the NEC code book allow you if you do a curve analysis on that one. So here's 100 amp on that one. And here's my conductor. Look at my conductor now. It's fully protected. Here's my damage. That's a damaged conductor. That's when, if you reach this point, the smoke starts coming out of the insulation and the cover start melting. So you can see between you and this condition is a big fat circuit breaker sitting in between, right? Now, if your circuit breaker is not to pick or malfunction, your conductor will burn. I didn't show the feeders here. So that's one. I want to close that one and go directly into the 75. Here's my 75 cable. Here's that 75. What was the size of the 75? I can't remember what was 250, right? Was it 250? The 75. Here's a 250. I think look how bad over 250 if you go by the NEC code book. Same thing. If I can go to 250, I can go all the way up to 100 here. From 250, look at that. I'm going to go from 200 all the way to 100, and I have miscoordination here. But if I grab this, see, it's instantaneous adjustable circuit breaker, and I drop it slightly up here, adjust it so I have my 5, or I can have it 10 here set at 10 redraw. So I can go probably as low as, I don't know if 5 will allow me to go here, redraw here. No, 5 will not. So I can go this. I have 100 circuit breaker, 100 amp circuit breaker, HKD, that can take the job of 250, and I can prove that this motor, based on these characteristics, will be better protection with a smaller circuit breaker. So the sheet that you guys have is for people who don't have an SKM. If you don't have an SKM and you can't look at these curves and you don't know what the manufacturer of your equipment is, remember, these are Cutler hammer. What happens if I have a square D? It's going to act differently. They have a curve for a square D. So if you know your equipment ahead of time, who the vendor is going to be, you can really end up with a very small circuit breaker sizes, which means a better protection for your power system. Any comments, guys? Any questions?
We should all have access to power tools. There's a large number of people that had advanced training last year, so if you haven't had any training, then you have to talk to me and we'll do some training. Those of you that have had training and don't remember or need advanced help, then talk to one of the people that have the advanced training. Hopefully they remember, although I challenged two of them this morning, and either one of them could come up with the answer. What's that?
So that's all what I have for you guys in terms of motors. Any comments, any questions? I hope it wasn't too overwhelming or too simple or somewhere in between. Yep. I'm looking at the time. Okay, so next time, guys, I believe we're either doing transformers or HVAC equipment. I can't remember what the schedule is, so I'll do the same thing. I'll keep using SKM as part of checking for the NEC code book. Thank you.
California, we need to make sure, I'm going to say this every time, make sure you get your time.